Hello. Now I have just opened the piles software of Oasys, and now I just want to show you how I have done this work. Initially, you can just go for the units and you check that here I have just specified the unit as per my user friendly nature, and displacement is in mm, force kilonewton, length per level in meter, mass kg, and stress in megapascal. After that, you can just place this OK button, and after that, this is the analysis stuff. Suppose you want to go for the capacity calculation, then you can just select this capacity, and for the settlement you can also select this settlement, and this all remains same. You don't need to change anything. After that, you can just go for the capacity data. Here if you see, there is a three types of IS2911 is for the India code, and EC7 Eurocode 7 is the UK national annex that we have chosen. And after that, you can go to the next page. Here is the design approach that you in your coursework it was written that C1 combination and C2 combination should be done, and the pile type here I have chosen the driven, and I have already provided the reasons why I have specified the same. And after that, this the partial resistance factor, you don't need to change anything. You only need to just showcase the parameter, and the shaft resistance R1 compression is 1, base resistance for set R1 is 1, shaft resistance factor for set R1 tension is 1, and for C2 combination it is 1.5, 1.7 and 2 respectively. Then you can just select the enter, and after that you can go for the settlement data. In this, it is this two types of calculation method is being specified. One is the mean linear equation, and another is the TZ curves, and the TZ curves is being used for the finite element analysis, but here is we don't want to be a complex analysis, and it is being used for the most practical design case. But here we can use the mean linear equation. It's a very simple equation, and this Young modulus of soil above the top level of pipe and the below the level of pipe is being done, and the regions has already been specified. Rigid boundary level is -200 is the, and this region is also being specified that is the where the settlement goes to 0, and we have given such a large rigid layer that it will never reach the same. Poison ratio of soil is 0.25, and number of pile elements is 10. It means that it will divide the pile into 10 segments, and it will analyze the pile capacity as this at this 10 segment for the drawing the capacity curve or settlement. And number of increment is kept 1000, and the increment type is kept as load, and the print increment is for rate of 1 for every is 50 increment. This 50 increment, you can see that when our the graphic output will be coming, it will show that the force has been applied in 100 kilonewton interval. First 100, then 200, 300, 400, like that will go for the 2000 kilonewton. Then you can just place it the OK. And this is the pile properties. If you see the pile cross section, we have chosen the solid circular. There may be other types of pile that you can choose, but in our case the diameter is given 0.45 meter. Is a circular part, and the compression value is, you don't need to change this. It is in MPa that I have done. Suppose it is given here the kilopascal, then you have to convert it accordingly. And this is, we have not considered the pile to be under rim, and the pile head is free here because it's a single pile. If you have multiple piles, more than 2 or more than that, then you can go for the fixed head pile, and after that you can just put the next. And here if you see that although our pile length is 10 meter, if we want, then we can also select this, and we can only provide a single parameter, just like I just deselect this, and you find that here I can just give 10 meter. But in this case we have given the variation from 2 to 10 meter. This is because you need the pile capacity chart, and the pile capacity chart, you just want to know the capacity at each level, how the in the soil, how the geotech capacity is varying. So for that reason we have kept it 2 and 10. Number of increments we gave in 10, and the depth of pile below the top of the high soil layer we have given 0. if you see that our cutoff level is 2 meter, if you want we can also have modeled, we can give it here 2 meter, but it doesn't require, because if the pile lies from the granular layer, means below 2 meter from the ground level, then we can just also analyze the model starting at below 2 meter, and we can take it at a 0 meter ground level. So it doesn't matter, it depends upon you whether you specify 2 or 0, but the pile should lie below 2 meter because the cutoff level is given 2 meter. After that, here we have specified the 0.45 meter diameter that is being given in your Excel sheet. You can give it, click the finish button, and this material properties, if you see, this is the 100 metals I have specified in the coursework. There this on Marston. If you see the geotech report, it has a 100 shear strength cohesion part, top and the base layer. So we have specified the top and base layer, and you will find this will be reflected in the graphical output how the soil has been given this strength. And after that, the skin friction is calculated. If you see this ball density unit weight, it can be checked from the geotech report in the triaxial compression test. You can find this, or in if you see the plasticity index, you can also find this block unit weight. After this is skin friction, if you see there are 3 types where you can calculate. One is the skin friction computation by using the alpha, second is the QS, third is this by using the limiting value. We are not using this part. We are more easy to do with this alpha part. Alpha U is the formula, and alpha is the reduction factor, and we have chosen it as per the curve after Welton that is mentioned in this presentation. After that, you can go for the end bearing data. In this case, we have added the end bearing data. The formula is NC, coefficient of cohesion, that we have used it 9. It is generally being taken. After that, end bearing data QB, we have not used this. We can use it by deriving, by just extracting the data from the geotech, but it doesn't matter because we have 3 types of way of choosing it. So we have chosen the most simpler way and most generally being used in the real world, so we don't need to be more confused with getting into a complex analysis. So we have done it in a more appropriate way. And this ball density, you can also check it from the geotech report, it is there. And drain materials, you will see is a granular soil, because after the 2 meter, the first 2 meter is the cohesive soil, but the pile lies below the cohesive soil. So the 2 layer strata is the granular soil and the Marston. In the granular soil, the bulk unit weight can be checked from the geotech report, and the skin friction is earth pressure, and we have used the coefficient of K here, and the delta shine is same as the internal friction angle. If you check the our parameter in the geotech report, we have a SPTN value of 27.7, and it has been derived from this. It was given that if the SPTN one is corrected, n value is 22, then the internal friction used to come around 35. So if we are having 27, then in a more conservative way we have given the file 41, and we have also compared it with different correlation data from the density as well as the Young's modulus that is being given in the report, and find that this is more appropriate being taken. And if you see here, we have not used the end bearing because the pile rests in the Marston, it doesn't rest in the granular soil. So we don't need to put these values because it will not end bearing capacity is of no use here. Then we just close it, and after that we can have a displacement ready. This I have given 1 meter, but it doesn't relate to your coursework. This is being used in the cases when suppose we have some utilities below the soil layer, and we want that this pile displacement should not affect the or should not clash with this utility. In that case, we just give it 1 meter, so that we can just check that how much the soil is displacing, that is not influencing the utility. This doesn't require in the coursework. And after that is the convergence control data. It's just a software, how it's working, what is the tolerance, what is the error, what is the coefficient is taking, what is the iteration is taking. It is not required until and unless your results converges. After that, the soil profile, and we have, if you see that we have just assign a value 0 at the top most like granular soil, although it is in reality it is 2 meter below the ground level, but it depends upon us, as I said beforehand. And then Moston is given minus 2.9, because this you can see, check in the report how the soil has been layered. So the most appropriate and borehole data has been considered for this, and minus 10 meters given a Moston. And there's we don't anticipate any negative skin friction here, so we have kept it no. Then the groundwater, if you see that in our geotech report, it is given that 2.2 meter below the ground level the water table is there. So when we are analyzing below 2 meter, then we can keep it minus 0.2, and the unit weight of water is given 10 kg per meter cube. It's okay. And then static load, here if you see, we have given a 2000 applied load and A1 and A2 factor. This is a partial safety partial resistance factor as per the Euro code 7. If you see, we in this case it 2000 kN doesn't matter, because as I have already said that we have given the load increment, then it will start from 100, 200, 300, it will go till 2000. So it may be 300 or 400, it doesn't matter, but the maximum load it will reach here. If you had not given that increment load, then in that case this analysis would have been for only single case. It will not have increment. It will this increment we have given because you needed the load capacity curve, load settlement curves. So why to do individually? It is easy to extract the data as a whole. So after this, you can just do the analysis, and if you see this warning is coming, but if you see, the soil will not be affected for this, as the layer of it is showing that CU is bottom is ignored, but doesn't get ignored because we have assigned third layer also. So there's a equal distribution of the layer. This you can just select the OK. Now you can find the tabulated output. Just a minute, just wait for this. Yeah, so you will go to this afterwards. Let's close it and just go for a graphical output. Yeah, if you check it, see, we have given a minimum length and maximum length, so that the pile capacity curve can be worked out here. And if you see this 4 tab, what is the maximum capacity the pile can take or the soil can able to resist. So this is the diameter of the pile. If you see, this is a design low tension. The tension is showing what is varying, how the from here to here how it is varying. And this is the ultimate low tension, like this is a compression, and then this is the ultimate compression. We can also get the value of it, but actually this is a varying, so it's not showing in this case, but it should we will do a different way. I'll show you. This is a pile displacement. If you see, okay, this is what has happened, that we have made a load increment, so we need to increase it so that we can find it in a better way. This is the pile length. I have checked it at 10 meter. Later I have given load increment 100, and the maximum load that I have we have assigned that it will come. Then let's see. what's the value? Yeah, the point is that here the value is not showing. We can just also get it from the report as well. If we had added individual, I will show it. If we had added individual, we do not have changed the length or change the load, then it could have shown easily, but it doesn't matter. See the pile displacement, soil displacement will come. This is pile stress, this is the skin friction, this is the limiting side friction. I will show you in different way. Okay, first of all I can show you this way. So if you see, this is the way that I have added in the report. You can also just add it here, there's no issue. You can just also correlate what is the capacity from this also. If you see, our 10 meter is the pile depth, and so it is 1800 is coming. It is coming now. Is the end, when just a minute. See, design capacity, it is coming 820 something. It will find the same in the report as well. Ultimate capacity is 1800, and design capacity tension is 450, 480, 490, and ultimate design capacity is 800. So this is here also you can find it, and graph also you can check it. In this way you can interpret it more easily. And in tabular output, if you can see, you can also find in all the details. I have also attached the files, the software files in I have given to you. You can just attach it for the reference of them, but it should be in the appendix section. If you see, all this data, as I said, is there in the input file, the factor as well. This, see, one by one you can see, you can understand all that I have said is being written here. But the major part, if we see, the important part is that, see, the soil layer it is showing is the skin friction and the stress. See, the factor that we have used here is the soil profile, there it is calculated. So the important point is that if you see here the compression result, okay, see here 838 at 10 meter height. So when you want the pile capacity curve with the depth, means if the depth increases, you see the capacity also increases. That is the pile capacity curve that I have attached. This is for the compression. This is for the different load combination. This is for the different load combination C1 and C2. So basically I will show a similar way how you can easily find out. See here the settlement. Here see the if you see its length is 2 meter, so settlement is showing abnormal value because 2 meter it doesn't make sense. We'll go for the 10 meter. Six 6.8. See here the length is 10 meter. This is displacement here. This is the base pressure. On increment of load it will go on increasing. See now it will come 6.802. See here 6.01 it was. Load increment 800 now, so 6.8, then 850, 7.664. So if you see 8.88, it's okay. The displacement is increasing with increasing load and the length is kept same. Okay, and here is the base displacement. The load settlement curve is done from here with different load. different displacement according to the graph is plotted. Where the graph gets constant or shows abnormal value, that's the failure point, because the stress does not increase. See here 2.7 MPa, here 2.7 MPa means the here the stresses means to certain extent the displacement increases but stress remains constant. Prior to it, if you see here 2.7 2 see 2.5598, after that previously if you see 2.3491, means constantly from above it was with increasing load, it was increasing, stress was increasing, but at a certain point it has become constant, means the point means it is the failure point. Now the soil or the pile won't resist any much load. So from here we have just worked out the load settlement curve, and the pile capacity I have already mentioned, if you can see, and I have done another file that I will show you. Yeah, in this here if you see the value will come. See, so this value are similar to the pile capacity that I have considered. And if you see the pile displacement, see here the pile displacement is showing it is something 0.23 something it will come, because the graph is 0 to 10. So this is all that I have done. Any doubt you can just ask.